Here is something that happens in almost every engineering team at some point. A developer needs to connect an application to a database. The connection requires a password. The password needs to be somewhere the application can read it at runtime. So the developer puts it in the configuration file, runs the application, confirms it works, and commits everything to the repository. The password is now in version control. It will be there forever, not just in the current state of the repository, but in every commit that comes after it, and in every clone that was made before anyone noticed. Deleting the file does not remove it. Overwriting the file does not remove it. Creating a new commit that removes the password does not remove it. The only way to remove a secret from Git history is a destructive rewrite of the history itself, which breaks every clone that exists, which in a team environment means coordinating a process that most teams never complete. That is one storage decision, one moment, a lasting consequence. The way secrets get stored determines not just who can access them today, but who might be able to access them at any point in the future, sometimes years after the original decision was made. And because most storage decisions are made quickly, under pressure, in the service of getting something working, the long-term access implications are almost never the thing being considered. Storage is not a single decision. It is a spectrum. At one end, secrets stored in plaintext in locations that are broadly accessible, configuration files in repositories, hard-coded strings in source code, values in shared documents, environment variables set manually on shared servers. At the other end, secrets stored in hardware security modules where the secret never leaves the hardware at all, where access is logged at the cryptographic level, where even the operators of the system cannot read the values stored in it. Everything in between is a set of trade-offs between accessibility, operational complexity, and the size of the population that can reach the secret. Environment variables occupy an interesting middle position that is worth examining carefully because they are widely recommended as an improvement over hard-coded secrets and widely misunderstood as a sufficient solution. The recommendation to use environment variables rather than hard-coded configuration comes from a legitimate observation. Environment variables separate the secret from the code, which means the code can be shared or published without sharing the secret. That separation is real and it matters. But environment variables do not protect secrets, they relocate them. The question of who can access the secret shifts from who can read this file to who can read the environment of this process, which in many deployment architectures is a much larger population than people assume. In containerized environments, environment variables passed to a container are visible to every process running inside that container. They appear in the output of process inspection tools. They are frequently captured by application performance monitoring agents, by debugging libraries, by error reporting frameworks, any tool that introspects the process environment to provide context for diagnostics. Aggregation, in an environment variable that gets captured by a logging agent and forwarded to a centralized log store, is a secret that has traveled from a controlled environment into an aggregation system whose access controls are almost always less strict than the application. This is a pattern that appears so consistently across real breaches that it deserves its own name: secret laundering. A secret starts in a reasonably controlled location, a well-intentioned operational decision. Better logging, better debugging, better observability moves it somewhere that appears equally controlled but has a fundamentally different access model. The secret is never deliberately exposed. It arrives in the wrong place through infrastructure doing exactly what it was designed to do. Dedicated secrets managers exist to close the gap that environment variables leave open. The core design principle is straightforward. Secrets are not stored where they are used. An application that needs a database password does not hold the password. It holds a reference, a path, an identifier, and retrieves the actual value from the secrets manager at runtime over an authenticated and encrypted channel. The secrets manager logs the retrieval. The secret itself never appears in the application configuration, its environment, its logs, or its deployment artifacts. This design solves several problems simultaneously. Access to secrets is controlled and auditable at the secrets manager level, not at the level of wherever the secret happened to be copied. Rotation can happen in the secrets manager without updating every system that uses the secret, because those systems retrieve the current value at runtime rather than holding a static copy. And the blast radius of a compromise at any individual service is limited to the secrets that service was explicitly granted access to retrieve, rather than everything in its configuration or environment. But secrets managers introduce their own failure mode that is worth naming directly. The secrets manager becomes the most sensitive single point in the secrets architecture. Its own authentication mechanism, the credential that grants a service the right to retrieve secrets, is itself a secret. If that credential is exposed, or if the access policies in the secrets manager are misconfigured to be too permissive, the abstraction inverts. Instead of limiting access to secrets, the secrets manager becomes the mechanism through which an attacker accesses all of them at once. This is sometimes called the secret zero problem. Every secrets management system has to answer the question of how the first credential, the one that unlocks access to all the others, is protected. Hardware-backed identity, platform-attested workload credentials, and strict network-level access controls are all partial answers. None of them are complete answers. The secret zero problem does not have a clean solution. It has a hierarchy of progressively better mitigations, each of which shifts the problem rather than eliminating it. The practical consequence of all of this is that storage security is not a property of any single decision. It is a property of the entire chain, from where a secret is generated to every location it ever reaches, including the locations it reaches accidentally, through logging, through debugging tools, through operational tooling that was never designed with secrets in mind. An organization that uses a secrets manager for primary credentials and environment variables for secondary ones, with logging infrastructure that captures both, has not solved the storage problem. It has solved part of it and left a gap whose size it probably has not measured. Most secret storage assessments count the hardened locations. They do not count the soft locations where secrets arrive through normal operations. The first question worth asking about any secret is not where it is stored. It is everywhere it has ever been, and whether any of those places have access controls that match what the secret actually protects.